Hi, so this is our first of two videos on, oftentimes students think, ugh, I thought I was taking a human biology class, why am I learning about chemistry? But I do want to remind you that remember that bio builds on itself, and truly chemistry or understanding atoms and molecules is really that smallest level of organization that we need to understand in order to understand things like tissues and organ systems. So in this video, I'm going to cover information from chapters 2.1 and 2.2. In this lecture specifically, we will be talking about atoms. We'll be talking about what atoms are and what their characteristics are. And really important for us, we're going to talk about also what types of bonds atoms can make, because really we can't have molecules unless atoms can come together to create those molecules. So let's go ahead and get started with atoms first. So atoms are really tiny pieces of matter that truly are considered the building blocks for all life. And this is really where biology starts, is at the atom level. Atoms are considered matter. Matter is anything that takes up space and has mass. And atoms are the smallest unit of matter that we know of today in science. Atoms themselves are made of smaller building blocks, and we call those building blocks subatomic particles, meaning that they are sub or lower than atoms, so they're smaller than an atom. And those three subatomic particles that build an atom are neutrons. Notice that neutrons typically have no charge, so think neutral neutron. We also have protons. Protons are positively charged. And if you look at the anatomy of an atom here on the right, you'll see that neutrons and protons are found together in the center of an atom, and that center point is called the nucleus. And the third building block that is required to make an atom are electrons. And electrons, they don't exist in the center of the cell. They actually kind of float around in this what is called electron shell or cloud. And electrons are negatively charged. So we have neutrons that are neutral, protons that are positive, electrons that are negative. And it's really the electrons, together with the protons, that really give each atom its kind of distinguishing features. But I do want to kind of point out some different ways in which atoms can be drawn, because you'll see these kind of throughout your textbook. So on the left-hand side of this figure, I have the same figure that I showed on the previous slide. And this figure is really considered the three-dimensional representation of an atom. Specifically, we're looking at an atom of helium. Helium is made of 2 protons and 2 neutrons that again live in the nucleus of the atom. And then floating around in 3D space are those negative electrons. Different atoms have different numbers of electron shells. So notice for helium, we really just have kind of this one outer shell. But if we compare that to oxygen over here, oxygen has 2 shells, one shell here and a second shell here, and we find electrons in both shells. More often than not, you'll see atoms represented in their 2-dimensional representations, which are in figures B and C. So rather than showing that these electrons can move kind of all over in 3D space, we just show them kind of sitting in different cells. But again, the protons and the neutrons will always be found at the center in that nucleus. And then some other things that I want to point out that we'll get into more detail here in a moment are that it's really the number of protons that determines really everything else about an atom. Notice, for instance, helium has 2 protons, whereas oxygen has 8. And so it's really the proton number that kind of tells an atom what it is. And typically, the number of protons is equal to the number of neutrons, which is equal to the number of electrons. We'll see that that can differ, but if we're talking about a general atom, all 3 of these things are equal to each other. So atoms themselves can make what are called elements. Elements are, as a definition, is considered a pure form of matter. And so an element of carbon, for example, is shown here in this figure of coal or diamond. That element is made of only that one type of atom. So the element of carbon is only made from carbon atoms. An element of hydrogen is only made from hydrogen atoms. So an element is just really a pure form of matter. And oftentimes, rather than talking about atoms individually, we talk about elements instead. So when you hear me say carbon, usually I'm talking about the element, but you can know that I'm also talking about atoms of carbon because atoms make up elements. Scientists have organized all of the known elements in what is called the periodic table of the elements. And you can see all of those known elements organized here. You really don't have to memorize this, and if you ever need it, I will always give it to you so you can reference it. But this is a really nice way in which elements can be organized based on how many protons they have in their nucleus, also their kind of chemical characteristics and things like that. Kind of the biggest defining characteristic is notice that elements highlighted in yellow are considered nonmetals, where elements whose boxes are blue represent the metals. And then we have kind of what are called the transition elements here in the center. And then we have kind of this dark line here that separates the metals from the nonmetals. But what's really important that I care about you knowing in the periodic table of the elements are these numbers here, the number that we find at the top and at the bottom of each element's box. So again, the name of each element is typically abbreviated either to the first letter of the name or the first two letters of the name, and often the name is coming from the Greek version. So for instance, iron, which is abbreviated Fe, comes from the Greek word like ferrous, which means iron. So sometimes the names don't fully make sense, but I'll always tell you kind of the full name of the element and its abbreviation. But let's look in more detail at these top numbers here. So if you notice, every single box in the periodic table of the element has a number above the abbreviated symbol of our element name and a number below that symbol as well. The number above is called the atomic number, and the atomic number always tells us the number of protons that are present in that atom or element. So for example, carbon always has 6 protons. The atomic mass, or the mass number, you can either name is interchangeable, is found at the bottom here. And the atomic mass tells us the overall sum of the mass from protons and neutrons. Notice if we look at table 2.1 here from your textbook, notice that protons and neutrons, they both have mass. They specifically have a mass of 1 atomic mass unit. Electrons, they have a little bit of mass, but it's basically 0, so we just say that it's negligible or 0. So really what the atomic mass is measuring is the sum of the protons plus the neutrons that we find. And we have decimal points because sometimes on average, this is kind of a sum of the total number of all of the elements we've ever discovered. So we can range, it's not always perfectly 12. But for carbon, we will always see that the atomic number will always be 6 because to be carbon always has to have 6 protons, and the atomic mass will be about 12, and that's again the protons plus the neutrons. So if you look at that periodic table of the element, you'll see that every element is defined by both of these numbers, by its atomic number and its atomic mass. The atomic number will never change. When proton number changes, the type of element we're talking about changes. So a carbon atom will always have 6 protons, never have any more or less. If it gains protons or loses protons, it will become a completely different element. But sometimes the electrons, which I often abbreviate as E-, and the neutrons, those numbers can differ. So sometimes we won't have exactly 6 electrons in carbon or 6 neutrons in carbon. So there are times when we do change that number. Isotopes and radioisotopes are an example of when we have atoms that have different numbers of neutrons. So an isotope specifically is an atom whose neutron number is not equal or is different from the atomic number. Kind of sticking with our example of carbon, there are actually 3 isotopes of carbon that we know of in nature, or at least that naturally occur in nature. And that's carbon-12, carbon-13, and carbon-14. Notice that to be carbon, all of these isotopes always have to have 6 protons. So the atomic number is never changing. However, notice that as we look at these different isotopes, the neutron number is changing. So carbon-12, carbon-13, carbon-14, these numbers are actually referring to the atomic mass, or they're referring to protons plus neutrons. So carbon-12 has 6 protons plus 6 neutrons, which gets us 12. Carbon-13 has 1 extra neutron, 6 and 7, which gets us to 13. Carbon-14 has 6 protons and 8 neutrons. So it actually has 2 extra neutrons, which get us to 14. Typically, though, remember that in our atom, our protons and our neutrons live together near the center of our atom. So when we start adding neutrons into that nucleus, that's going to cause this kind of region of the atom to become very crowded. And things don't like to be crowded, just like humans often don't like to be packed in like sardines. It's the same with our subatomic particles. So there are times where we can have what is called a radioisotope. Basically, what has happened is that in radioisotopes, so many neutrons have been shoved into this nucleus that we have created a nucleus that's very, very crowded. And because of that, this nucleus becomes unstable. And we can consider that the atom that is made up by that nucleus is unstable as well. And because it's unstable, it's going to start releasing radiation. When it does that, it's trying to make kind of this living situation more comfortable for itself. But that radiation can be dangerous. If you've watched like the Chernobyl show on HBO, for example, we know that we had this nuclear radiation event and it's really dangerous and people can't go near it. But radiation can also be used to our advantage. We use radiation to take x-rays, for example. We can also use radioisotopes to examine potentially cancerous tissue. So for example, we can look at a person's thyroid gland by giving them, basically they can eat a radioisotope, and that radioisotope can kind of organize itself into the thyroid. We can use that radiation that's being released by those radioisotopes to take an image, and that allows us to measure the size of the thyroid gland. So we can determine if the thyroid is kind of like a normal shape, like we see on the left, or an enlarged shape. So radiation in small amounts can be really helpful for science. However, there are times, again, where it can be very dangerous. In the example of a sunburn, like we see on this woman here at the beach, sunburning, the burning of your skin from the sun is actually because the sun is releasing radiation and it's damaging your skin, and your skin is becoming burned because of that. So we have good and bad radiation. Most of the time radiation is dangerous. It's only safe when like really controlled and in very small amounts. So we have atoms. They are made of protons, neutrons, and electrons. Typically, protons are equal to the number of neutrons, are equal to the number of electrons, but we do have times in the case of isotopes where that neutron number can change. Now what I'd like to talk about, though, is the fact that atoms often don't exist just on their own, and instead they want to come together to create what are called compounds. So for the last kind of half of this lecture, we're going to talk about how atoms make bonds. So in general, elements of different types can come together by creating chemical bonds. So to give you an example, and oftentimes when elements make bonds, they can be very different in terms of their properties. So to give you an example is this figure here, where we have the element sodium, and the element of pure sodium itself is actually a solid metal. And it's very, very reactive. If you put water on sodium, it literally will explode, as shown in figure B here. So it's very reactive with water. Chlorine is an element made from just chlorine atoms, and it forms this yellow gas that we can see in this Erlenmeyer flask here. However, we commonly know of a compound called NaCl, or salt. This is the table salt we use to season our food. When we combine an element of sodium and an element of chlorine, that's when we get sodium chloride. And this compound is very different from its elements. When A, it's not a gas anymore, B, we've all added salt to water, NaCl to water, and we've seen that it does not explode like this when we add it. So when we create compounds, we have combined two different elements. Usually those elements are always combined in very specific ratios. And in the case of sodium chloride, or NaCl, we've created a compound that acts very different from its independent elements. But let's actually talk about how atoms create bonds in the first place. So creating bonds has to do completely with the electrons that live in those electron shells. So to focus first on the figure here on the right, we have three atoms. We have a hydrogen atom, which has an atomic number of 1, and it just has this one little electron floating kind of in its outer shell. Carbon has an atomic number of 6, so it has 6 protons. And we also see 1, 2, 3, 4, 5, 6 electrons total. And notice that there are 4 electrons in the outer shell. So notice this atom has 2 electron shells, 4 electrons live in that outer shell. And then oxygen, its atomic number is 8. It has 8 protons, 8 neutrons, and 8 electrons if you count all of these. Again, those electrons are kind of separated between 2 electron shells. We see 2 in the first shell, and we see 6 in this outer shell. So there are 6 electrons that live here. These electrons that live in the outer shells, they are what play a role in creating chemical bonds. And it's these shells that are going to allow atoms or elements to make compounds. So it's important to know that different electron shells can hold different amounts of electrons. The total number of electrons that the first shell can hold, for example, is 2 electrons. So notice that for carbon and oxygen, their first shell is full. They have 2 electrons that live in that first shell here. The second shell can hold up to 8 electrons. So notice that carbon, it only has 4 electrons in its outer shell, and oxygen only has 6. It can hold up to 8 though. So notice that both of these have basically unfilled shells. So they have openings in their shells where they could fit more electrons if they wanted to. There are some atoms that also have a third shell. It's not shown in this picture here, and the third shell also holds 8 electrons. But really the whole goal is when atoms create bonds, they want to try to fill that outer shell. So carbon, it wants to gain 4 more electrons so that it can have an outer shell that holds 8. Oxygen wants to gain 2 electrons so that its outer shell holds its maximum value. So when the atoms are making bonds with each other, they're trying to fill those open seats, essentially. So let's look at some examples. One of the most common types of bonds that we are going to talk about are called covalent bonds. And I really want you to think of covalent bonds as the let's share model. In this situation, atoms are going to share electrons in order to fill their outer shells. So in this example here, we have carbon. Again, it has 4 electrons in its outer shell, so it needs 4 electrons for that shell to be full. Remember, hydrogen has only 1 electron shell and only 1 electron living there. And remember, the first shell can hold 2 electrons. So each of these hydrogen atoms needs 1 more electron in order to have its shell be completely filled. So what can happen is carbon and hydrogen can say, well, hey, why don't we just get together and we'll share electrons? Specifically, we're going to have 1 carbon atom to 4 hydrogen atoms, but notice that when these atoms start to share bonds, they make it so that they overlap their shells. So notice that this hydrogen atom has 2 electrons living in its outer shell. This hydrogen atom has 2 electrons living in its outer shell. So now every single hydrogen in this case is happy. And by sharing, that also helps carbon. That notice if we look kind of from the carbon-centric view, carbon also now has 1, 2, 3, 4, 5, 6, 7, 8 electrons sitting in that outer shell. And so now all shells are filled. And now all of these atoms are very happy because they have filled their shells. Notice that this drawing that we have here, it's kind of a complicated way of drawing this process out. So oftentimes covalent bonds are just shown by a line. So notice that we just have the letter of our atom, C for carbon, H for hydrogen, and then we just have lines connecting those letters showing that a covalent bond or a sharing of electrons has occurred. So let's look at another example. So we've just created the compound methane or CH4, but sometimes the sharing isn't always equal. In general, if we were to look at the periodic table of the elements that are listed kind of on the left-hand side, those can be considered weak. And as we move to the right, the strength increases. So these elements here on the right tend to be stronger, meaning that they can hold on to electrons stronger. Typically as well, from the top to the bottom, the electrons near the top are weak and the electrons near the bottom are stronger. So if we were to say make H2O or water, we'd be asking oxygen, which is a really strong atom because it's farther to the right, to be making a bond with hydrogen, which is really weak. It's all the way to the left and at the very top. So when we have atoms of different strengths trying to share their electrons, that sharing is not going to be equal. What that means is that one of those elements is going to pull harder or hold on to electrons harder than the weaker element. So we can still talk about the fact that we're making covalent bonds, we're sharing electrons. But there's 2 new terms that come into play that help us explain what's happening with the sharing of electrons. And those terms are nonpolar and polar. When you hear the term nonpolar covalent bonds, that's telling you that the atoms in that compound are sharing electrons equally. So we have an equal sharing of electrons in a nonpolar covalent bond. Polar covalent bonds are the opposite, where we have unequal sharing of electrons. The thing that always kind of helps me to remember the difference between polar and nonpolar is really think of, honestly, like our current political situation. We often talk about, oh, those 2 people are polar opposites, or, you know, our two political parties are very opposite. They're polar opposites. Like Democrats are this way, Republicans are this way. And we talk about people being polarized or having very different opinions. So just think polar is different or unequal, which means we're going to be sharing, in the case of atoms, our electrons unequally. Nonpolar, we don't have a difference of opinion, so we're going to share electrons equally. We've seen examples of nonpolar covalent bonds already with CH4 and carbon dioxide on the previous slides. But another example of a nonpolar covalent bond is of oxygen gas, the oxygen that we need to breathe. Two atoms of oxygen have equal strength, and so these atoms will create specifically a double bond between them, but they're going to share atoms equally. What's important to keep in mind about this is that this compound as a whole has what is called a neutral charge. Or you can think of this as having a zero charge. That's not going to be the case when we talk about polar covalent bonds. So to give you guys an example of a very common polar covalent bond, let's look at the molecule water. So water is formed by one oxygen with its 6 electrons here, and it's going to form bonds with 2 hydrogen atoms, which they have 1 electron. So they're going to create these bonds here and here. And we can just draw water as looking like this when we talk about its covalent bonds. But if you look at your periodic table of the elements, oxygen is far to the right and hydrogen is far to the left. So oxygen is much stronger than hydrogen. So what that means is that oxygen is going to really pull on the electrons that are being shared, and that's going to make both of those negative electrons look like they're closer to that oxygen molecule. So really think of a game of tug of war. Oxygen's going to win here, and it's going to pull those electrons really, really close to it. Remember that electrons are negative. So oftentimes what happens in a polar covalent bond is the stronger molecule ends up looking partially negative in terms of its charge. We show partial charge by drawing this funky little s. It's the Greek letter delta, lowercase, and we write negative. And that tells us that this area of our molecule is partially negative in charge. The hydrogens, because they are weaker, they are going to kind of lose that negative charge of their electrons. And remember, hydrogen has 1 proton. Its atomic number is 1. Protons are positively charged, and so the weaker elements in our bond are going to look partially positive. So in polar covalent bonds, our compound is no longer neutral. Our compound is charged. Where some areas look a little bit negative, some areas of our compound look a little bit positive. And that's really important, especially when we get into our discussion about water. So polar covalent bonds create compounds that have regions of partial charge difference. Nonpolar covalent bonds, no charge difference across the compound. So covalent bonds, atoms are sharing electrons. There is another type of bond to keep in mind though, and those are the ionic bonds. And you can really think of ionic bonds as the let's borrow method, where rather than sharing electrons, we're going to see that one electron actually just completely is borrowed from one atom to the next. And a really common example of this is with our molecule that we've already kind of briefly talked about, sodium chloride. So in sodium chloride, notice that both sodium and chloride have 3 electron shells, 1, 2, and 3 here, and 1, 2, and 3. Remember that the third shell can hold up to 8 electrons. If we look at sodium, notice that its third shell, it only has one electron sitting in that shell. Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons. So it's almost completely full. So instead of sharing electrons, what can happen is chlorine, which is a very, very strong atom or element. If you look, it's all the way to the right-hand side of the periodic table. It can say to sodium, hey, look, we'll both be happier if I just take your one electron. If I borrow it, my shell will be full. You'll no longer have any electrons in your third shell, but your second shell is full. So if I just steal your electron, we'll both be happy. And so that's what happens here, is notice that this electron is going to hop over to chlorine. Chlorine now has a completely full shell and it's happy, but sodium, even though it lost an electron, its second shell is now full, and so it's also happy. But something has happened. Remember, electrons are negatively charged. So when that electron hops over to chlorine, that chlorine now has an extra electron. So the overall ion becomes negatively charged. Sodium has lost a negative charge, and so because of that, it now has an unequal number of protons and electrons. So that positive charge of the protons is going to show through and create a positively charged ion. An ion is an element that has a different electron number compared to protons. So isotopes were changing the neutron number, ions were changing the electron number. So now we have a chloride ion that has an extra electron and it's negatively charged. We have a sodium ion that's lost an electron and it's positively charged. But that's really great because now this positive and this negative charge can be attracted to one another. And that's when we create an ionic bond, where now these oppositely charged ions can come together to create a compound of sodium chloride, or NaCl, or table salt. So by borrowing electrons, we're creating or causing our elements to have opposite charges, and those opposite charges then bring our elements together to create a compound. So covalent bonds, we're sharing electrons to create a compound. Ionic bonds, we're borrowing electrons to create a compound. So those are the two kind of big bond differences that I want you guys to be aware of for this class. There's tons of videos on YouTube as well if you want kind of an extra visual. But something I would also like you to do is for kind of the next section of lecture, rather than create a PowerPoint slide for you guys to watch, I'd like you to watch a YouTube video from the Amoeba sisters that I've posted on D2L that helps explain the properties of water. I've also made a Word document that I've organized to kind of help you take notes as you watch that video. So use that provided handout. But watch that video on water, and then your second video will discuss kind of the last bit of chemistry that I want to go over, and we'll talk about the key molecules that are required for life.